Evaluation metrics for different tasks. There is the coefficient of determination, R square. There is mean squared error. For the classification case, you have F1 score, accuracy, precision recall, ROC, AUC, and so on. Okay. And we also looked at the confusion matrix. Um, Again, I asked the same question last time. What should be the ideal values for false positive and false negatives? If you have a perfect model available with you, what should be the type 1 error and what should be the type 2 error? It should be 0 and 0. Okay. Uh, because you'll always have the correct predictions where correctly you would have gotten true negatives and true positives instead of false positives and false negatives. Okay. Um, yeah. Looking at the naive-Bayes classifier, it is a probabilistic classifier. If you have read your probability, you might know about the Bayes theorem, right? So here, what it defines is given an event X, okay, what is the probability of Y happening? Okay. So let's take an example, okay, where you flip a coin. Okay. Let's say X is talking about an event where when you flip 2 times and both of the times you got head. Okay. And let's say Y is an event where you calculate the probability of getting tail. Okay. So if I frame it according to the Bayes theorem, what I want to know is what's the probability of getting tails? Okay. When I've gotten two consecutive heads together. Okay. So this is what I'm meaning. So it's conditioned on some prior event. Okay. And I mean, there are probabilities. This is your posterior. This is your prior. You don't need to get too much into the mathematics here. I mean, there are a lot of different concepts involved. Okay. But yeah, this is the basic idea. Where given an event that has happened, what's the probability of another event happening? Okay. Very simple example is the coin toss. Okay, there is another example, okay, where you have an individual named Jane who will go, who wants to take a test to determine if she has diabetes or not. The overall probability of having diabetes is 5%. Okay, so anyone taking the test, okay, anyone taking the test would have, I mean, the overall probability is 5%. But if she obtains a positive result from her test, okay, we should also update this probability, right? To account for this additional information. She has also gotten a positive result from this test. And then it becomes our posterior probability, posterior being this one. Okay. Prior is this. So how does knife-based classifier work is you calculate the prior probability for given class labels, find likelihood, calculate posterior, and see which class has the highest probability. Okay, let me explain. Okay, how do you calculate? How do you calculate things? Okay, so given the weather, okay, you're going to predict whether you're going to play or not. This is a very simple example. If it's sunny, you might play. If it's rainy, you might not play. I mean, there are different data points available with you. Okay, what you do is first you calculate the frequency table. Okay, frequency table for each event. Okay, you calculate the frequency of class labels. So if it's overcast, how many times there is no? There is zero, so I've left it blank. How many times I've said yes? Okay, it's four. Uh, and similar to other categorical features. Okay, you calculate how many times there is no, how many times there is yes. You basically populate this whole table. And what do you think should be the dimension for this table? What should be, how many weather attributes should be here? So how many ever unique examples that you have? So only there is sunny, overcast, and rainy. So that's why it's only three. And this should be the number of class labels. You only have yes and no. There is no maybe also. Okay. So only no in yes. What do you calculate is the likelihood. Okay. For overcast, you calculate the probability of S given the total number 4 by 14. Okay. It's 3 by, then it's 5 by 14 for sunny. For rainy, it's again 5 by 14 because the sum 3 plus 2. Okay. And total observation is 14. And same way you calculate it for no and yes also. So total 5 by 14. For yes, it's 9 by 14. So you got the individual, okay, probabilities here. You got it for overcast in total, you got it for sunny, you got it for rainy, and you also got the probabilities for no and yes. Okay. Here again, what do you do if you want to calculate the posterior probability? You for if you are calculating it for no, so if it's overcast and no, the probability is zero. For overcast and yes, it's 4 by the total number of yes you have, it's 0.44. Okay. Again, for sunny, it's 2 by the total number of no's, that is 5. Very similar, you calculated for rainy and everything. So you got all the probabilities with you. Okay. And then when some other new point comes, okay, you check. Let's say your, let's say now I'm saying it's sunny. Okay. Here the probability for no is higher. Okay, it's 0.4. The probability for yes is lower. So whenever it's sunny, most likely you're not going to play because this has higher probability. Now, let's say suppose the weather is rainy now. Okay. What do? You check again, you check the probabilities. The probability for no is higher than probability for yes. So again, your prediction will be no. This is how you make predictions. Okay. And why uh, can anyone give me the meaning of why is it called naive Bayes? This is the Bayes classifier turned into naive Bayes. And it's better to use it when you have categorical input variables instead of numerical ones. And to be specific, use cases being text classification and recommender systems. So given a data point, it's also very easy to predict the class based on these probabilities. Okay. Anyone has any doubt? Should I explain it again or no? Any doubts? Or was it too complex? I mean, even if you don't understand the math, it's fine. If you look at the programming, it's easier. You just have to import the class from scikit-learn and then apply it. Okay. Okay, moving on to support vector machines. And this is an algorithm that can be used for both classification as well as regression. Okay. Let's say you have two different classes, the green points and the blue squares. Okay. I want to find a line between them, okay, that can separate it best. Okay. I would say whatever point lies to the left of this line, I'll classify it as green. Whatever lies to the right of the blue squares, it will probably be classified as blue. Okay. So where do you think I should draw the line? Okay. I can draw a line here, I can draw a line here, I can draw a line here, I can draw a line here. What should be, where should I place this line so that I can have better accuracy from my model? Where do you think? Where should I draw? So this is called a decision boundary. So where should I draw it? Just take a guess. Where should I draw it? Take some time to think. It's very easy actually. You can guess it from this diagram also. Okay. Don't you think it should be exactly in the middle here? Okay. Because I need some enough space so that even if a point lies here, it should be classified as a green circle instead of a blue square. Okay. So this is called the maximum margin hyperplane. The distance you have is called the maximum margin. And how do you calculate this distance? You take whichever point is at the end, like this point and this point. These are called your support vectors. Okay. You draw lines here. Okay. This is the negative hyperplane, meaning whichever is towards this side, it's called a negative point, and whichever is towards this side, it's a positive point. Okay. Exactly in between. Okay. Exactly in between you draw a line. This is your decision boundary. See, again, a data set has two features, x1 and x2. These are your classes. Okay. And see, there are multiple lines that can separate. I can do it like this, I can do it like this. How many number of lines do you think can I draw here? How many number of lines? Just any guess. So there can be infinite number of lines that can be drawn. Okay. And yeah, this is the goal of SPM is to maximize this margin. Okay, you have to find support vectors and you have to maximize this gap between the optimal hyperplane and the support vector. That is the goal. Okay. Any doubts till now? I'll wait for some time. Any doubts? Okay, no doubts. Moving on. Okay, here I'll talk about the ML pipeline. Okay, how do you do something called hyperparameter tuning? What was the hyperparameter that I talked about in k nearest neighbors? there was one thing that I changed, right, in the model. It was the value for K, right? Okay, that's what I changed. Why did I change? Because with each K value, you get different performance, different accuracy scores for your model. Okay, and you need to find the K that gives you the best possible accuracy to you, right? So this is where hyperparameter tuning comes into the picture. Okay, so what you do is you do something called K4 cross validation. Okay, you have a data set like this. If you are doing five-fold cross validation, you split it into equal parts. Okay, into five equal parts. Let's say I have 100 data points. Okay, if I'm doing five-fold cross validation based on this particular picture, okay, how many data points should I have in my train set, and how many data points should I have in my validation set? So there should be 80 data points in train and 20 in test, okay? Because you're splitting it into five equal parts, so there'll be 20 in each. So you take four for training, one for validation, okay? And you keep changing the validation fold. If it's five fold, you get five different accuracy scores. And at the end, you average and get the performance, okay? And what you can do is you fix, let's say in the K nearest neighbors, you fix the value for K, okay? Do this, check your performance, how it is, keep track of it, okay? Let's say you change the value from 1 to 20. And based on the graph that I showed in the previous class, 13 was the best, okay? So what you do is you can peak the model performance based on these hyperparameters. And this is a very important step, okay? Choosing the appropriate value is very crucial for getting the best possible results, okay? Once you have the best hyperparameter values, what you do is you train your model again based on the training data. And finally, you have your model that is trained, that is the best possible performance that you can get based on these set of hyperparameter values, okay? So what do you get from this graph, okay? What do you get? So this is called a parallel coordinates plot, okay? Just see the plot, guess what each should be. What are these things? Why do you see these lines? Just tell me. So what you can see here is this is a hyperparameter, this is another hyperparameter, this is also another hyperparameter. So you have three different hyperparameters that you want to check for your model. And this is the final performance metric. It can be accuracy, it can be FN score, it can be anything related to your task. It can be R square, it can be mean square error, and so on. Okay. So I have different combinations to try among these things. Okay. I have different combinations. I want to try every combination. And as you can see, let's say initially I didn't do any hyperparameter tuning. I choose 0.0430. Okay. My model performance came out to be around zero point 0.3 only. It's not very good. Okay. Then I tried 0.0440 and this gave me around 0.85. Okay. So you think maybe increasing this value can give me better performance or decreasing this value can give better performance. Okay. Ultimately, if you look at the higher scores, it's like the LR value is around zero point 0.3, the category value is around 3.4, and LRDK value is around 0 and 0.1, 0.01. So this is what hyperparameter tuning uh, gives you, gives this information there, which particular combination of the hyperparameters gives you the best possible performance. So this is hyperparameter tuning. So this is the overall thing where the flow, okay, is demonstrated. What you do is you can search from different hyperparameter search methods. Okay, you can select different hyperparameter search methods. The grid search is the one that I talked about here, where you test for all possible combinations. But what is the problem with grid search? Anyone? What do you think the problem will be with grid search? Because if there are many number of hyperparameters, and for each hyperparameter you have a lot of things, okay, there, or if you take all combinations, it's like very costly. Okay, you can't run all the models. Okay, each combination you can't keep testing it again and again. Okay, so you can use something called Bayesian optimization or random search, where you only search randomly and get the, you might get the best possible combination or you might not. Bayesian optimization is also the case. There's also always a trade-off between the runtime and the best possible hyperparameter combination that you can get. Okay, if you do more runs, there is better chance of you getting the optimal values. Okay, so what you do is do cross validation for each fold, train your model, calculate accuracy, get the average, and assign the average accuracy to the current hyperparameter set or combination you're trying. Okay, then you select the hyperparameter set with best possible accuracy score, go through one of these search methods again, then do the search again. Okay, this is the whole thing being repeated again and again. Okay, it keeps repeating again and again, either when all combinations are tested or you have set like you have predefined the number of trials that you are going to do. Let's say only I want to test only 100 hyperparameter combinations, so the loop keeps on going until it reaches that limit. Okay, this is is what all is about hyperparameter tuning. In summary, yeah, two new algorithms, naive Bayes and SVM. An I-base is called the ideal classifier. SVM is uses the maximal margin hyperplane. And you should always think about making hyperparameters for your optimal results. Okay. Yeah. Any doubts?
மேலே விளக்கு பொருத்தி வச்சது எங்கெங்க விளக்கு போடுறோமோ விளக்கு பொருத்தி வைக்கிறது.
Then if there are no doubts, we can end the meeting. Thank you.